Hi everyone. Today we're going to be looking at section 7.6. We're going to break this up into two videos just due to the fact there's quite a few different variations to these calculations and problems. So we're going to look at solubility equilibrium and the solubility product constant. So we have to do a quick little recall of what exactly is solubility from the start of this chapter. So we know that solubility is the amount of the solute that is going to be dissolved in a given volume of solvent, and it always takes place at a specific temperature. So solubility tells us how much solute is present in a solution at equilibrium. So if we consider this reaction of solubility where we place sodium sulfate solid into water, okay, this equilibrium is established. So what exactly is taking place here? So on the onset, when I place these sodium sulfate crystals into water, the barium ions and the sulfate ions are leaving the surface of the solid and they enter into the solution. Initially, the concentrations of these ions is very low, and so therefore the forward reaction, which is dissolving, is occurring at a much greater rate than the reverse reaction, which is recrystallization. Eventually, though, the rate of the recrystallization and the rate of dissolving is going to become equal. When this occurs, we say that this system is at equilibrium. So you'll notice that the reactants and products in this particular system are at different phases. And so therefore the reaction is said to have reached a heterogeneous equilibrium. Okay, these equilibrium that we're studying now are heterogeneous versus the ones that we've looked at so far have been homogeneous, where all of the reactants and products are in the same phase, meaning they're all in gases or an aqueous state. So for solubility systems of low soluble ionic compounds, equilibriums exist between the solid ionic compound and its dissociated ions within the solution. So we can express this as an equilibrium constant expression. The same way we would do when we figure out equilibrium constant expressions for homogeneous expressions, all right, where we solve for K. So for this particular reaction, the equilibrium constant expression, K, would be equal to the barium ions and the sulfate ions for this particular reaction divided by the barium sulfate solids. So we can ignore the concentration of the solid barium sulfate and it gets incorporated into the equilibrium constant K. All right, so if you recall, that's what we were able to do. So I'm going to incorporate that K barium sulfate solid into our value of K. And so when we do this, we actually call this KSP because it's specific to solubility. And what remains for this KSP is just what is found in the numerator. For this particular reaction. So this equation gives us what we call the solubility product constant, KSP. All right, that's what this stands for. The solubility product constant. Okay, which is the value of the equilibrium law equation for the solubility equilibrium. The subscript, the SP, distinguishes this constant from the general equilibrium constant K. So as with K, KSP is calculated using concentrations in moles per liter, and KSP values are not given units. And so quite often these KSP values are tabulated through experimentation, where we gather all the data and we can provide them on reference tables. We do have such a reference table in our textbook on page 725. That gives us a very short list of some of the solubility product constants for some common ionic solids. So the KSP then, don't forget, we always need to make sure, you'll notice that when we give these values of KSP, the temperature is always going to be included when reporting the solubility product constant KSP. All right, because it does vary with temperature. All right, so let's take a look then at an example of how we use this. Look at some sample problems. So in this first example, we want to find the KSP for calcium fluoride at 25 degrees Celsius, given that we've got 1 liter sample of a saturated solution. So this is very important that we've got a saturated solution. It's evaporated to dryness and it produced 26.76 milligrams of solid calcium fluoride. So let's record what pieces of information we've been given. Okay, so we've been told we've got the mass of the solute, which is my calcium fluoride, and we're told that it is 26.76 milligrams. But right away I see that it is in milligrams, and so don't forget this is at equilibrium, because we know that we've got a saturated solution. And since it's in milligrams, I need to convert it right away to grams, because anytime we do any concentration calculations, we need to make sure things are in grams. So I'm going to divide this by 1,000 to get it converted into grams so that I have it handy when I have to do my calculations. So it's dividing it by 1,000 and we get 0.02676 grams. So because we got to find concentration, the other piece of information I'm going to need to know is the molar mass of calcium fluoride using my periodic table. All right, so I'm going to using my periodic table. I find that it's 78.1 grams per mole. Using this information here now, I can find the number of moles, remembering that moles is equal to mass over molar mass. This is using some of our grade 11 information and prior knowledge. And so we've got our mass in grams. We just found our molar mass. And this is now going to give me my moles, 3.43 times 10 to the negative 4 moles of calcium fluoride at equilibrium. Now we can find the concentration. Okay, so C equals N over V. I just calculated my moles. I know that my volume is 1 liter. So it's 3.43 times 10 to the negative 4 moles over 1 liter gives me a concentration of 3.43 times 10 to the negative 4 moles per liter. All right, so this is at equilibrium, okay, because we're talking about a saturated solution. So there's a bit of prior work here that we have to do before we can start finding the KSP. So our next step is we're going to set up an ice table first, just like we do in any of our equilibrium problems. So we're going to set up an ice table. And we're going to let X represent the change. Okay, so we have to start with our calcium fluoride it dissociates into our ions of calcium ions, aqueous. So I got to write the dissociation of this ionic compound in water. And it produces 2 fluorine ions. We got to make sure this is a balanced equation here. All right, so when it dissociates, it breaks down into 1 calcium ion and 2 fluorine ions. So we're going to set up our acronym ICE. Now, because this is a solid, we do not incorporate. Remember, my calcium fluoride solid is incorporated into my KSP value, so we do not include that in our ICE table. We start off with no ions of both calcium and fluorine ions, and the change is we increase it with plus X, and here we increase it with the factor of plus 2X. So 0 plus X is X, and 0 plus 2X is 2X. Now we're going to set up our equilibrium law expression. So KSP is equal to the concentration of my calcium ions and my fluorine ions to the power 2. All right, now since there's a ratio since my calcium fluoride ions to my calcium ions, the ratio is 1 to 1. Okay, so then X, which is the concentration of calcium ions, is equal to 3.43, which we calculated, times 10 to the negative 4 moles per liter. This equals the concentration of the calcium ions at equilibrium. Okay, which means now I can find 2X. To calculate the fluoride ions. So 2 times X is equal to 2 times the 3.43 times 10 to the negative 4 and this is going to equal 6.86 times 10 to the negative 4 moles per liter, which is equal to the fluorine ions at equilibrium. So now that we have both values, we can plug them into our equation. So KSP equals 3.43 times 10 to the negative 4, and 6.86 times 10 to the negative 4. And when I work that out, KSP equals 1.61 times 10 to the negative 10, and this is at 25 degrees Celsius. All right, so that's the KSP value for this particular problem. All right, so we found the KSP value. All right, so we do have to recall some of our grade 11 formulas in order to calculate and have some of our information that we need on the onset. All right, so let's take a look at the next example. This time we're doing the reverse. We're going to be given the KSP value, and our job is going to be to find equilibrium concentrations. We're finding the solubility. So it says find the molar solubility, so that's sort of the key there. They tell you that it is 25 degrees Celsius for calcium oxalate, and they give you this already. If I didn't give you the KSP at 2.3 times 10 to the negative 9, you would have to look it up on a reference table. So I would have to provide you either with the KSP constant or a reference table where you would be then looking for this value. So you got to find the molar solubility, and molar solubility is in moles per liter. And then the second part is we want to find this concentration in grams per liter. All right, so let's do the first part of this question by finding the molar solubility. Okay, so step 1. As always, you got to set up an ice table. Okay, we're going to set up an ice table and let X represent the change. All right, so we're going to have to write the dissociation equation for calcium oxalate. Usually we give this to you, but otherwise you have to work it out, making sure you find all the correct chemical formulas for each one. So calcium oxalate is CaC2O4 solid, and when it breaks down into its respective ions, it's calcium ions and oxalate ions. So this is a 1-to-1 ratio. So again, we set up our acronym ICE. Because it's a solubility, we do not include the reactant because it's a heterogeneous. On the onset, there are no ions of products, and we're changing it with respect to a factor of X. So it is X as our, at equilibrium, it will be a value of X. Okay, so step 2, we're going to set up our equilibrium law expression. So I'm writing out the steps, so when you're doing your homework you can refer back to these examples. Set up an equilibrium law expression, which is my KSP, and this helps us to find X. Okay, so KSP is equal to the calcium ions and oxalate ions. Okay, so we know our KSP, it's been given to us in the question, it's 2.3 times 10 to the negative 9. I know this is X times X, so I'm just going to call it X squared because X times X is X squared. So now to solve for X, all I do is take the square root of both sides to get my value of X. So X then equals 4.8 times 10 to the 5 moles per liter. So I've answered the first part of the question. And so this is the molar solubility at 25 degrees Celsius. All right, the molar solubility for calcium oxalate is 4.8 times 10 to the negative 5 moles per liter. Now in part B, you're being asked to find how many grams is this in 1 liter. So we're looking for the mass. All right, so we're given from the question here, we know that we have 4.8 times 10 to the 5 moles. Okay, this is our moles. So this equals N. And we got that from the concentration in the previous question, the molar concentration. So we need to, therefore, in order to do this, we're going to need our molar mass of calcium oxalate. So when I look that up using my periodic table, I get 128.1 grams per mole. Now I can find the mass. Okay, so mass, if you remember from grade 11, is number of moles times the molar mass. I was given my mass. My moles is 4.8 times 10 to the negative 5 moles. And the molar mass I found for the calcium oxalate is 128.1 grams per mole. And when I work this out, I get an answer of 6.14 times 10 to the negative 3 grams. This represents the mass. Okay, so what this tells us in, therefore, the molar solubility of calcium oxalate at 25 degrees is 4.8 times 10 to the negative 5 moles per liter. And in 1 liter of water, only 6.4 or 1/4 times 10 to the negative 3 grams of calcium oxalate will dissolve. So we've answered both parts of the question. So this is a bit of a reverse of the previous question. All right, so folks, your homework then is going to be to try on page 462, numbers 1 to 3, and page 464, numbers 1 to 4. All right, good luck, and we'll see you in the next lesson, part 2.